Ok. Prova, sì, ok. So, before we start and we go ahead with the quadruple, I just want to clarify two things. Is it okay? Yeah. So first of all, I want to correct something wrong that I said yesterday, and shame of all of you. The only person that noted this was not, no offense, the youngest of the student, Leonardo. So, but we define this quantity, and I said that it's traceless, which is clearly not. It's trace reversed, because if you do the trace, is h bar is equal to h minus, and so this is minus, minus h, okay? So it's trace reversed. And, but in the TT gauge, so the one that we came at the end to express the final form in which the 2 degrees, radiative degrees of freedom appear, you remember that h bar was traceless, so in this case even h become traceless. The second clarification that I wanted to make, probably a point on the stress energy tensor. If you remember yesterday, we wrote our G mu nu as actually, well, K T mu nu. And then we split both G mu nu and T mu nu in terms of the perturbation and the background quantities. Okay, we did this in flat space-time, so T bar, what we call the background, was basically 0, and the delta T was basically, so our delta T was really the perturbation that was inducing the gravitational waves, okay? But you can consider that, you can take this as a very general, I mean, we can consider different situation in which both T bar and delta T are different from 0. And actually, delta T has two contributions. Yesterday I mentioned it briefly, but for example, you can have a metric which is this, where this G mu nu is not only a black hole, so a vacuum solution, but could be, for example, a black hole surrounded by dark matter or something like this. There are some solutions, okay? And then you put an external perturbation, so a delta T, which could be given, for example, from a particle, okay? You have like a very small particle such that their mass ratio, m over capital M, is much smaller than 1. Okay, so it's really like a particle affecting lightly the background geometry. Okay, and in this case, the full delta T will be given by two contributions. Delta T mu nu, let's say, of the black hole plus, in this case, let's call it Dark-matter halo, plus delta T mu nu perturbation, where this is the particle. And this guy here would be basically delta T that goes on top of the T bar, so the background. So in this, what I'm saying is that you have this G mu nu, okay, which is this black hole with some dark matter halo, in this case, some accretion disk, whatever, okay? And this G mu nu solution is, solution of the background equation, this, okay? Where this T mu nu would be, for example, the matter outside the black hole. Okay, you perturb this because there is like a particle, a small black hole going around. This ignites the emission of gravitational waves, and you will have the delta T, will have then two contributions. This, which is the particle sourcing the perturbation, but then I have what I call delta T black hole, which is the perturbation of this guy here. Because even this one will oscillate, will have a perturbation with whatever are its variables, fluid, pressure, density, and whatever, okay? So in a more general system, of course, you have to consider that your at the linear order, delta T can actually include contribution even from the background perturbation and not only from the source of the perturbation. Of course, for us, this wasn't happening because T bar was 0, so there was nothing to perturb there. Okay, this is a general, you would find the same for a star, okay, in which you have fluid modes. Okay, instead, something that, this case, for example, a non-rotating black hole with accretion disk around, or a non-rotating black hole with a spherically symmetric distribution of matter. I can give you an exact solution for that. I mean, analytical. Okay, going back instead a bit on the basis. So what we want to do is finishing today the quadruple part and discuss the actual form of H for a binary system. So yesterday we arrived to this. And sorry, I'm a bit slow today, but I'm sick. So our Einstein equation supplied by the gauge conditions, and we saw that basically this gives basically 2 degrees of freedom and radiative. And we saw that, I will just make a recap, that our general solution written in terms of retarded integrals was this. And actually that in realistic scenarios, where our source is located way far from us, so basically x prime is the coordinate which is integrating over the volume on which the stress energy tensor is different from 0, and x basically is the vector pointing to from the source to the detector. And since for us we are assuming, and actually give you some numbers later on just to be concrete, we saw that this can actually be written in this way. Well, I can actually put it outside over R. Yes. Yeah. It's here. This is the solution. As you find in electrodynamics, when you solve like the Lambertian, and there is actually the 1 over CD in the T, that time goes here. Is the fact that your solution is retarded. Okay. All right. Okay, just to say, we won't prove it, but this also automatically satisfies even the gauge condition, okay? You can take this as an exercise, but if you plug this solution, this comes directly from here, but if you plug this inside here, you will find like an identity there, which basically show that this solution actually solve immediately your problem. Okay, what I want to do now is that this looks a rather, I mean, you can of course prescribe your whatever stress energy distribution, which source your Einstein equation, yeah. Covariant. Yes. So you can prescribe your T mu nu, and this you can use this to compute it. I mean, to compute your H, the components, the 2 components of H bar. But there is a nice way to express this in terms of what is called like the quadruple moment of the source. Okay, and this is gonna be the main topic of the lecture here. And to do this, we are in flat space time, so let's do this. Let's compute, let's start from our the divergence of T mu nu equal to 0, that in this case really means conservation of energy and momenta. So, and if you expand the coordinates here, you get this expression, the I, where mu goes from 0, 1 to 3, and I is 1 to 3. So we can integrate over the volume of your source, so you get 1 over C integrate. Okay, this is I. And then you can use your, what was it, the divergence theorem, for which basically this is equal to minus T. This is basically the divergence of this guy here. And then basically you can write this as T mu I dSi. And I wrote this as dSi basically is Ni ds. So the infinitesimal element, and then this Ni is basically the vector which is orthogonal to the delta S. And then you can use basically, let me write it as a V, and this is the surface element. You can basically, we have sources which basically have a fall off rapid enough such that they vanish at the boundary. So basically the flux here is completely zero. So you have that this guy here is equal to 0. So you have that 1 over C, the integral over is equal to 0, which basically tells you that you have a 4 vector of conserved quantities. You know, I think that you have seen this many times. So this one. This is because basically you are assuming that your source has a compact support, and basically you have at the boundary, the domain is large enough that at the boundary it goes to 0. So there's no matter basically at the surface. Yeah, yeah, of the surface. Yeah, yeah. Exactly. This is integrating over the boundary of all the source term, and basically you have that the source goes to 0 at the over the surface. So you have a quantity, a vector of quantity which is constant. Okay. Now, okay, we've just redone something that probably we've seen already in special relativity or wherever, but you can immediately see a connection with what we wrote here, because we have that the integral over V of T mu 0 in the 3x is constant, which is exactly what we have here. Okay, so basically this tells us immediately that H bar mu 0 is equal to constant. Okay, and we can actually put this constant to 0, because for us it's not interesting, because we are looking to propagating solution that depends on time. So these for us will not be of interest. Remember that we are solving for wave equation, so something basically that has a wave-like character, or in any case has a dependence on time. This conservation tells us that there is a subset of H mu nu, which is H mu 0, so all the time mixed components, which are constant, and I'll put it to 0 and I won't consider it anymore, because at the end of the story they won't matter for us, okay? They won't contribute to the radiative, so the things that propagate in time. Okay, we can do the same trick for the spatial component and find something even more interesting. Which is the following. So let's take again the T T n 0 equal to minus di T n I, and now both n and I goes 1, 2, 3. So I'm taking the full spatial version of the T mu nu comma nu equals 0 equation, and let me integrate again over the volume. Actually, let me integrate again, but before the integration, I'll multiply on the y on the left and on the right hand side on a coordinate xk. Okay, so I'll write this, and I'll write this in this way. Okay, just taken this, multiplied the left and right, and integrated over the volume element. Okay, let's work a bit on this. I can use my standard rules of integral by parts, and I'll write this in this way. When I make this will be the derivative of this minus the derivative of the x, but of course the dx k over dx I, this is delta ki. Okay, so this just changes the nothing, just changes I into k. Vabbè, this basically we've already seen it because this again is the divergence of something, a vector here over I. So I can do the same trick as before. I'll write this as an integral over the surface. I'm assuming that T mu nu is going to 0 fast enough on the surface. So this thing here will be 0. And so what I get is this equal to this. Now, by construction, the stress energy tensor is a symmetric object, which basically means that if I take this, the integral over t kn in d3x over v is exactly equal to this. Okay, we agree? Because I mean, t mu nu is asymmetric to rank tensor. Okay, so this, if I just, this expression, I take this expression, I flip the indices, I see what is like here. So this guy here now will be 1 over c, the integral over v, d t, t k 0, xn in d3x. The two are exactly the same, so I can actually sum up the two, and let me write this in this way. The integral over v t n k d3x is equal to 1 over 2c this. Okay, I know that this is symmetric, so this thing here, that equation allows me to write this. I just flip the indices, but then this is exactly equal to this, so I sum it, I get a 2 in front that I bring to the other side, and this is the final expression. So I get something that for now is nice, but useless, so that the integral over the source term of the nk components is proportional to the derivative of something, I mean, whatever it is. I'll put it there on top, keep it, and let's go ahead. Okay, now instead of these, let me take the 0 component. So here we take the n0 and ni component, and instead let me consider these components. I will still be 1, 2, 3. So we'll still run on spatial indices. And let me do exactly the same trick as before. So I'll integrate over the source term with abuse of notation here. So I'll get tt, t0, 0, but I'll multiply on the left and right hand side by xk, xn, and then I'll do this. And the same on the right hand side, minus okay. Okay, and let's do the same kind of trick that we did on the right hand side. So we'll write this as a V, the I T0I xk xn d3x, and now then we will get two contribution, because this will be plus the integral of T0 k xn plus T0 n xk. Okay? V. The indices here just come every time that you hit one of these coordinates with the corresponding derivative, and you get a Kronecker delta. Okay? This is the same as before, is the usual divergence. We use the divergence theorem, we evaluate this on the boundary, 0. So, at the end, what we get is that 1 over C d in dt T00 xk xn d3x is equal okay? We are close, because if you look at this expression here, look there, we are almost the same, because on the left hand side, on the right hand side of both expressions, there is something that is very close each other. So what we can do now to bring it even further and to bring even closer is that we take time derivative of that thing there. So we write this as a 1 over c squared d in dt squared over t00 xk xn d3x is equal to the integral over well, 1 over c okay? And then we're basically done, because modulo some factor of 2, we have that on the right hand side we have exactly the same expression. So we can actually equate the two. And so at the end of the story, we get that 1 over c squared d squared over dt squared we have this expression, so that the integral over the spatial components of the stress energy tensor I just took the time derivative of the left and right hand side, because I have the time derivative there, and so I want to make the two expressions look the same. Okay, since now the two expressions are the same on the right hand side, I can actually equate the left hand side. So I have that this thing here now with the second derivative is equal to that thing on the right, on the left. Okay, which is this. This tells you that the integral over the spatial components of the stress energy tensor is the second equal to the second derivative of in time of something that is basically called the quadruple moment of the quadruple tensor, because as integral indices here of your source. So I cancel this, let me leave it here. I'll actually call no, they're orthogonal, so they will be 0. So here I get, let me write in this way, that d in dt squared q n k of t is equal this, where the modular factor of 2, this is what I wrote there as q. Okay? Tell me. Which big Q? Ah, the one that we introduced, yeah. In this case, this is a general quadrupole tensor. That case there was the tidal induced quadrupole tensor, but they are different in this case. Yeah. This basically is the quadrupole tensor of your stress energy or matter energy distribution. So you have a matter energy distribution, okay, and if it's not spherically symmetric, it will have like a certain quadrupole tensor, which is given by this. Okay, and then, since we've written this, you can connect this with our expression for the gravitational waves, which is there. So we can finally write that we found that these components are 0, so they're not propagating. The mu0 for mu equal 0, 1, 2, and 3. And the remaining component there, which are purely spatial, can be actually expressed using this equation here. So h n k will be 2g c to 4, 1 over r, d square dt square, q n k t minus r over c. Okay? So this is the quadruple formula for the gravitational waves, for the amplitudes, and which basically tells that the components that are actually propagating are the spatial ones and can be expressed in terms of second derivatives in time of this guy here, which is the quadrupole moment of the system, which is given by this expression, modulo factor of 2. Okay? And this is extremely nice because we'll also simplify a lot our calculation that we will do in very short for the binary system. Okay, let's keep it there, but this I think I can cancel. You have this on your, well, let me put it there. Let me make a couple of notes. That I think are interesting besides the mathematics behind this thing. The first one is that if you see, yes, ask me in case you have, it's better to talk each other all together. This is T R minus C. Okay. This is because it was X minus X prime, but I mean it's, okay. So the first note that we want to make is that if you see the gravitational wave have a coupling in front, which is this guy here, and this is this number, if I made the correction, the conversion correct. So it's something which is 10 to minus 50 grams minus 1 second square centimeter. So it's a very, very small coupling, which tells you that the amplitude in general is extremely weak. And so basically you need a Q to be very, very high. I mean, for sure now I'm producing gravitational waves, because I mean, I should have a different from 0 quadrupole moment, especially when I'm moving, but I mean, I'm not energy dense enough to produce something measurable. Okay, so you need something that burns order of solar mass energy, like in the coalescence that we have seen, in order to make something observable. Okay. The second thing, very nice, is that, and we will see then in practice, but that the gravitational wave components depend on the motion, the features of the matter, energy distribution, velocity, motion, but not on the force they produce at them. Okay, so just on, you have something which is its motion. I don't care about what produced that, but the features of those, of that motion is what gives me the stress energy, perturbation different from zero. And the third, that you can make here an analogy, and you can actually draw the differences with respect to the electromagnetic sector. So in the electromagnetic case, if you have two charges, you will have or not even, like a collection of charges. You can have an electric dipole moment given by this collection of charges, and which depends on time if you have like moving charges, and P, the power emitted, will be proportional to the second derivative in time of D. In our case, we are actually going one moment further. So basically, the gravitational waves are not of dipole nature as electromagnetic waves, but the leading contribution is given by the quadrupole. And this, you can see this immediately, because if you have a collection of masses, you can always define something that can be like the gravitational dipole, but in a system of in an isolated system, like the linear momentum is conserved of this guy, so d dot g will be constant, and so basically its derivative will be zero. So conservation of momentum for a collection of masses will set d dot equal to constant, so will not contribute to the emission, whatever its derivative. No, I'm just trying to make the difference that while in the if you take charges, the leading order contribution to the emission will be given by the dipole of your system, and indeed the power will be second derivative of this. In gravity, you don't get this, because basically for an isolated system, like, your momentum is conserved. Okay, so any time derivative will be zero. So you need to go like a moment higher in your tower, and indeed you see that the h mu nu is not a dipole, but it's a quadrupole at the leading term contribution. It actually tells more, since that h mu nu is the second derivative of the quadrupole. First, if you have like an object which is perfectly spherically symmetric, this won't emit gravitational wave because the quadrupole is zero. But even if you have something which is axially symmetric, so has a quadrupole moment, it has to have a time varying quadrupole moment. So something with a quadrupole moment, which is constant in time, still will be zero in terms of gravitational wave emission. So you not only, you need a certain degree of asymmetry varying in time. Quadrupole is still not enough. You can have like a constant, an object with a constant quadrupole moment, which won't give any gravitational wave emission. This also, for example, tells you that if you have like a star which is collapsing by like a sort of like spherically symmetric in each time collapse, they won't emit any gravitational wave. Okay? So you need this asymmetry. And indeed, this asymmetry is what we're gonna look for. But before going to so what I want to do now, or at least in the next hour, is transform this, which is a general result you can apply everywhere, but to a specific case, which is the binary motion of 2-point particles. Okay. If you want to see some other example, for example, I'm sorry for the repetition, you can look, there is a book written by Ferrari, Pani, and Gualtieri, and you can actually see there are different examples. For example, one of the nicest cases, what's the gravitational wave emission in case of a rotating star? And indeed, you need, in order to make gravitational wave emission, that your star is rotating with a certain, the principal axis of rotation should be actually inclined with respect to the moment of inertia of the star to have an asymmetry such that you produce a time-dependent quadrupole moment. So I strongly suggest to look at that book for other examples. We will focus and specialize on binary system. But before this, I want to give you like a prescription to project things in the TT gauge. So basically, we have seen that the coordinates can be a bit misleading because the actual physics may not be evident in one coordinate system with respect to another one, and in particular that the real radiative character of gravitational waves, where you identify clearly that there are only 2 degrees of freedom propagating, is the TT gauge, okay, which passes through like the two well, imposing the harmonic gauge and then removing like the residual gauge of freedom corresponding to the homogeneous solution of box epsilon equals 0, if you remember yesterday. Okay, that looks a bit like you can always do that, but I mean there are easier way to perform this thing. Okay, so given a tensor, to project that tensor into the TT gauge without passing into solving for the harmonic gauge and then solving box epsilon equal to 0. And to do this, we introduce this guy here, a projector. This is a symmetric projector. So if I exchange the indices, I'll get the same. And then these, sorry, let me write this in this way. And J, this project any vector onto a plane orthogonal to an I. You can check this because if you take a generic vector Vj and you do Pij V, you get Vi minus Ni and J Vj, okay? And then if then I do this Pij Vj Ni, so I project this onto the normal n, I should find 0. Yes, yeah, sorry, I didn't say this. This project any vector into the plane orthogonal to n. And indeed, if I take this vector, I take the projection, and then I try to compute the scalar product, I should get 0, which is exactly what I get, because I get this. This is 1, so this is 0. And also, P square V is equal to PV, or if you want to write this in terms of coordinates, these are all identities that if you want, you can try to alone by prove, very easy. And then that Pi, J, and J is equal to 0. The same for I, but that's symmetric, so. Okay, I introduced this because then I can define a projector on the TT gauge as Pijkl as Pik Pjl minus Pkl. This basically, if you take a tensor And we're gonna see in a second, and you apply these, so you project this tensor using this projector, you're gonna extract the transverse traceless part, which is the one that by end yesterday we show corresponds to the degrees of freedom of gravitational waves. If you remember, yesterday we wrote at the end the matrix for gravitational waves emitted in a certain direction, and that matrix had only two components that we call the plus and cross polarization, and we saw that it was transverse to the direction of motion, and the trace of the thing was equal to 0. If you want to project H immediately, okay, on that gauge such that the H mu nu becomes immediately transverse, so orthogonal to the direction of propagation, and trace free, you take H and you project H using this. I'll show you how, but so without going basically on all the machinery of setting the harmonic gauge, finding the differential equations and the solution and blah, blah, blah. Now, the sum of these properties of D, of this P, I'll close with this, and then we're gonna make this 5 minutes break. Don't worry. Which lambda? No, the big lambda, you mean this lambda matrix? No, these are the coordinate transformation matrices. So if we want to change like a vector Vm, some coordinates, you write this like this. Oh, I don't remember. Okay, maybe if you show me, yeah. Okay, so it's transverse. So this object, the projector there is transverse. So if you do is equal to 0, and this holds on non-indices. So don't let me write it, but if you do, instead of I, you do nj or nk or nn on these, you'll get exactly 0, the same. And then it's traceless in this sense, because it's an object with 4 indices. That if you compute the trace over the first two or the last two indices, you'll get 0. And finally, the most important thing for us, that if then I want the Hij in the TT gauge, instead of passing through solving for the harmonic gauge, I'll directly do this. So projecting my tensor or using this P will immediately give me the TT version component. Sorry? Yeah, at this level, yes, because everything is on flat space-time. So this TT means, as we said yesterday, so trace-free and orthogonal to the direction of propagation. As correcting what I said yesterday, we show today, if I remove the trace, so the trace is 0, H and H bar will be the same. So doing this is exactly equal to do this. And so, at the end of the story, and I'll leave probably this to the blackboard, in order to write our gravitational wave amplitude h mu nu in the gauge in which the two degrees of freedom are manifest in their radiative character, and they are also trace-free and orthogonal to the direction of propagation, these will be equal to 0, and these will be our expression before, in which our Qij will be written in this way, where this object here is just Pij KL QL T minus RC. Okay? So if I want to project immediately, and we will see this, the quadruple tensor into its TT version, We're going to compute these in the coordinate frame that we like the most, and then we're going to use this projector in order to go into the gauge that we need to make everything physically manifest. The last thing that I want to write is that sometimes is, you can find this in books, but it's also useful to define a reduced quadruple that I'll call with capital Q, which again is different from the Q that we saw yesterday at the, on the presentation, which is Qij minus 1/3 delta ij Q. I think I can claim safely that in this case the delta, the trace is 0, because it's Q minus Q in this case. This is just, everything is on spatial indices, and this is like the Kronecker delta. And you can check immediately that because it's extract, again, this capital pi, the projector on the TT gauge extracts the trace from the tensor. Applying this to capital Q or small q will be exactly the same. You can do by hand, but I mean, intuitively, I mean, since this is removing the trace from your tensor, and this is defined as this minus its trace, then the projector will be the same. Okay, I think that I will do 5 minutes of break, and then we're gonna do in the specific case of binary motion. Any question on this? Yeah. You have to go, well, you can do, yeah, you can do this in a more sophisticated way up to a certain point. I mean, like computing everything like on a general background. There are some very nice notes by, I'll at the end of the lecture, I mean, I will actually share the slides, and there are like some references including like a nice paper by Anna Flanagan and Scott Hughes on this, basically on gravitational waves on general background. So you can do the same, but I mean, augmenting everything with covariant derivatives. Or you can do like these post-Newtonian things that we were saying, which is similar basically, and you can move from flat space-time and then like add order by order corrections, and you will have like correction at any order in tensor derivatives and blah, blah, blah. This will be up to what you're looking. It depends on the system. If you're looking to a wave coming from X, Y, Z direction, and okay, so it's a direction perpendicular to the... It depends on the inclination, if you wish, between depends on the source. For example, for a binary will be like the plane, and then whether it's here, you're here, or you're somewhere in the angle between. I think, yeah, indeed. I think I have a couple of examples later. Okay, we come back in at 10 precise. Are gravitational waves emitted by a binary system? For sake of simplicity, we will assume that our binary, given by this sketch here, the binary is confined into the xy plane. Okay, we have a planar motion. So I have two masses, M1 and 2, that are going around a common center of mass. Let me write M, capital M, as the total mass of the system. And at this level, I mean, what we need to know is just pure Newtonian mechanics. And what we're going to do is basically use Newtonian concepts of two-body motion. So basically, going into the center of mass, you can define the coordinates of each particle, of each object, in this way, m2 divided by total mass, and L0 is the distance between, relative distance between the two. So let me write actually, probably, let me write it in the vector forms. And then I have okay, I jump into the center of mass and then I define the modulo of R2 minus R1 minus R2 as L0, so the relative distance between the two. Okay, we want to find, what I want to show now is which is the connection, which is actually related to a question that one of your colleagues asked yesterday. So which is the relation between the angular frequency of, if you wish, the velocity, the characteristic velocity of your system, and the frequency of gravitational waves. And the first thing that we need to find is finding the Keplerian velocity of your system. Okay, I can just write down the equation of motion of my system. And this gives me the Keplerian frequency again. L0 is the relative distance between the two. This is all we need, basically. Okay. Now, what I want to write now are the components of this in order to find the expression of Hij as a function of M1, M2, L0, and omega k. To do so, let's take this and let's write the coordinates of the particle, the two particles. I'll call it particles or stars, black holes, whatever. At this level, it doesn't matter. And let me write them, these coordinates, in a Cartesian frame. So I'll have x1 and y1, and this will be divided by m cos omega k t and then I can write the same for x2 y2 minus m1 m L0 cos omega k t minus m1 capital M L0 sin omega k t. Okay? Is the relative distance between the two bodies, so the orbital separation between M1 and M2. Okay, these are the projected Cartesian coordinates, the coordinates of the two objects. There is one thing that let's keep in mind now, because it will change later, that omega is constant. Okay, all our parameters are fixed by the particular orbital configuration that we are studying. So we have M1, M2, the L0 is a definite constant, which, I don't know, 10 million kilometers, 10 kilometers, whatever, but it's fixed. Okay, so omega k, the Keplerian frequency, is fixed. Okay, now we want to compute Q, and remember that, well, we cancel it, but the quadruple moment is what? The integral over the stress energy tensor of the system. So let's compute the stress energy tensor associated to this system here. We plug there and we see which is the expression for the gravitational waves. All right, so I'll write for a collection of particles, of bodies, as in this case, T mu nu I can write the stress energy tensor in this way. These are like the four momenta of the nth body, and in our case, n goes from 1 to 2, so our two balls there. This is the energy associated, okay? And this is the delta, which basically says that all of these needs to be computed at the location of each particle. Now, in our case, as I was telling you at the beginning, our objects are actually confined into the xy plane, so there's no d theta component, which basically means that, and if you remember, the quadruple tensor is the integral over T00, so we just need the 0, component of the stress energy tensor. So let's take the 0, component of this. So it's T00, that in our case is n equal 1, 2, C square mn I've just unpacked the P and the energy, okay? And since my particles are running on the xy plane, there is coordinate x, coordinate y, and zeta n is equal to 0, okay? They are here, moving. This is just the T00 component of the stress energy tensor. Okay, now let's compute the values of Qij. Yeah. There is, no, this is what the P mu will be M CV, right? This is everything will be special relativity at this level. So the più mi, yeah, if you wish, yeah. Sorry, there is a gamma factor here. Yeah, that at this order doesn't matter. Well, actually simplifies with this. Is it? Yes, yeah, I agree. No, this is this at the I think at this order. It's a weak field. See, sorry, I'm by indeed. No, see, there is a gamma, but there is this fact that we stated at the beginning. This is weak field. Sorry, in all this mess I was forgetting. Of course, we are in the weak field limit, so at this order it won't matter. The gamma here won't matter. Okay, thanks for the note. So let's now compute. You see the point that Nicolau was making, right? There is a gamma factor that in our, and indeed, actually, if you want to compute this at the next leading order with post-Newtonian, you should start taking into account all these terms. For us, at the beginning, when we derive the quadruple formula, we basically say that this holds in a weak field. The condition that the lambda gravitational, the wavelength was larger than the typical domain of the source was actually giving a constraint on the characteristic velocity that was smaller than the speed of light, if you remember yesterday when we started. Okay, which this. Okay, now let's compute the QXX. So I want to compute the XX component of the quadruple tensor, which is the integral over the T00 of my, over the volume of the source. And let me unpack the T00, so I will have this. Okay. This is just the definition of the quadruple, the XX component of the quadruple tensor. If you remember that at the beginning there was T00 multiplied by XA, XJ, and in this case, since I'm looking at the XX component, this brings me an X square. Okay, there are delta functions everywhere. I can integrate, and this will give me M1 X1 squared plus M2 X2 squared. Okay? Now, take the expressions that we defined there in Cartesian coordinates and replace it here. And if we replace it here, we're going to find, I won't do this by hand, but this is what we find. And actually, let me write this in a more comfortable way. I'll write it like this. So I'll use the, I never remember, like duplication formula of the cosine to write this cos square as cos twice the orbital frequency, plus there is a constant term. Remember that at the end of the story, we have the quadruple moment of the system, and we need to take two derivatives with respect to time. So this term here, I won't consider anymore, because when I will actually compute the gravitational wave, the second derivative will just kill this guy here. So the only things that matters is that the QXX component is given by this object here. And sorry, I didn't write that this is the reduced mass, which is this. There was a question? Okay, without replicating this thing, but you can actually compute all the other components, and you realize that there are only other two non-vanishing components of the stress energy tensor, well, no, of the quadruple tensor, and these are QYY and QXY. So all the other components will go to zero. The zeta component will all go to zero just because there is a delta, a Dirac delta peaked in zero. All the other term will vanish, and these, you can compute this by yourself. I mean, it's just really algebra, but you're gonna find that I will always have this form. So the only non-vanishing will be XX, YY, and XY. And here there would have been another constant term. So if you compute the YY, you will actually find that it's again like something proportional like this. And there will be, using the duplication formula, another constant term, which I can safely put to zero, because in the quadruple, then I have to make the second derivatives to compute the gravitational wave, so it won't really matter. Oh, also note that if you compute QKK, so the trace of this, it will be zero. The trace of this matrix, so of the quadruple tensor, will be QXX plus QYY plus Q zeta zeta. Q zeta zeta is zero. These are the only non-vanishing components. And the XX and the YY components have the same, are the same with a sign inverted. Yes? Did I miss a square? It may be, let's assume that there would be a 2. I'll check it later. It may be a typo, but yeah, thanks a lot. It may be, I'm not super sure. Yeah, I mean, the argument holds. Yeah, it may be that there is a typo here and there is a square, yes. Okay. Okay, just for the sake of convenience, also let's rewrite this small q in terms of the capital Q that we wrote before. And just because this is immediate, which thing I can cancel? Probably that. And so if I write everything in terms of just because since the trace is 0, I can directly work with this, and again, just for repetita iuvant, this will be the only 2 modular square here that could be. Let's put it, well, I think it is. No? You check it? Okay. I'll check it later. For now, let's go on with my notes and then. Okay, these are the only non-vanishing components. Okay, that's it, because now we can immediately assemble our gravitational wave amplitudes, because we take our formula. We know that the 0 mu components will be 0, will not propagate. And then in the TT gauge, our spatial components, did I miss something, Nicola? Oh. This is going to be 2G over C4R, d squared in dt squared, and then Pij KL, QKL, T minus R over C. Okay? This is what we've written before. So now the only thing, I'm going more specific because this is the expression that we wrote before in a pure general sense, but now we have the components of capital Q, which are those. So what we need just to do is apply twice the time derivative with respect to qxx, qxy, and qyy there. And if you do that, you're going to find that the expression is going to be like this. Okay. So every time that you hit those guys with a derivative, there will be an omega coming out, right? Because the only dependence on time here comes from omega t. So you make a derivative and you will have a change of sine and cosine function, and then you will have like an omega. So you hit the derivative twice, and you get omega squared. I'll write it at the blackboard in half a second. And then you have this A, which is this matrix here. Because now I have assembled everything into a matrix. It's just a way to write in a compact form. And indeed, let me write these for us will be what I could call like A KLTT, which is basically this matrix projected using the projector. And then this object here, did I define with the minus? Well, without. So without the minus sign, this will be the gravitational wave amplitude. Now, as I was discussing before, as your colleague was suggesting, This guy here in particular, AKLTT, depends on the particular orientation in this specific physical case of the orbital plane with respect to the line of sight. So where the detector is with respect to where the binary is happening. So for example, if n, so remember when we define Pij as delta ij minus, so if n corresponds with the zeta axis, then the Pij will just be diagonal 1, 1, 0. And I won't show here, but in this particular case, you will have that the waveform is circularly polarized. So it will have basically both H cross and H plus components. This depends really on the particular source and orientation, but if n is equal to y or n is equal to x, you will have Pij, which is diagonal 1, 0, 1 or diagonal 0, 1, 1. And we'll have that the source, the gravitational wave is linearly polarized, so you will have only one of the two components there. But besides this, that really depends on the particular binary and source configuration, there is an important aspect here, is that if you see, the gravitational wave frequency is twice the Keplerian frequency. So in this case, basically, you have the system as a characteristic orbital frequency omega k, which is our Keplerian frequency in this case, and the emitted signal has a frequency, or in this case a pulsation, GV, which is twice omega Keplerian. Okay? Now, the physical situation is that I have this thing on a particular orbit, and when it's moving on that particular orbit, it's emitting a waveform signal with that particular frequency, which is twice the Keplerian frequency, and scaling as 1 over r, and the masses, and blah, blah, blah. But what the system is doing is that it's losing energy and angular momentum, because, I mean, this thing is radiating, okay? So what this radiation comes, subtract basically orbital energy to the system. What you could imagine what happens is basically the system shrinks and shrinks more and more until it basically collapses. But this basically makes a very important thing, which is that your orbital elements that we have assumed to be constant, so omega k and L0, are not constant anymore. Because if the binary is shrinking, the orbital distance between the two objects is decreasing, and the gravitational frequency, or the Keplerian frequency per se, is increasing. Okay, this is the intuition. So what I want to show is actually how we can compute and relate this phenomena and actually compute the phase of the binary as the binary evolves during the coalescence. So it emits gravitational waves and it proceeds up to the merger. Okay. To do this, I need to give you a formula, I mean, out of nothing, but I really don't have time to do this, is that you can quantify, let's say, the emission of gravitational waves in terms of the gravitational wave luminosity, okay? So what you want to do is define the energy flux, the energy emitted by a gravitational wave, and I mean, you can compute, you can actually perform a rigorous calculation and find in a very, very general way, this is not related with this particular science case, so the binary, but if you take the energy emitted, the gravitational wave luminosity, so the energy emitted over time, this is basically given by this formula, which is the quadruple formula for the gravitational wave energy. So that was the amplitude, and this is for the luminosity. So it is proportional to 1 over C25, modulo this G. And it's basically the product of the third derivative of the quadrupole moment. Okay, so the amplitude is the second derivative and the power emitted is the third derivative of the quadrupole moment. And I define this as an average So to define the gravitational wave luminosity, you need to take that expression there, take, so basically third derivative, the product of third derivatives of the quadrupole moment components, and make an average over several wavelengths. This is the fact, this is basically related to the fact that in GR you cannot define like the energy locally, okay? And I can only define this basically through an average procedure. We don't have time to go through this, but this is it. But this average also basically implies that your orbital, if I'm doing average over like several orbital periods, I cannot allow my binary to change the configuration too fast. Otherwise, I mean, this average will be impossible to be done. Yeah. In this case, yeah, you can do exactly the same. This is a general formula. Okay, when we apply these, I mean, in this case, we're gonna do the circular case, but I mean, and indeed, the original Peter Matthews paper, so the one that compute, I think, the luminosity in particular for considering immediate 3D eccentricity. So, and in particular, this condition that we will gonna assume is that the orbital elements do not vary too much. So they are loosely speaking, we are emitting gravitational wave and the orbital separation is changing. But this process is adiabatic in the sense that it's changing slowly and not abruptly, okay? Of course, this is a simplification which actually will be true when the objects are very far apart. When you're gonna be close to the merger, this thing won't happen anymore because I mean we will have like a very fast spiral. And indeed, you need to work out a different technology, and basically also won't be impossible to solve the problem in a semi-analytical way. This condition is indeed what goes to the adiabatic approximation. Now, in this regime, no, let me take it there. Where do they write? For our particular case of interest, so for the binary, if you plug the values of the quadrupole moments that we found before, you take the third derivative, you will find that LGW is this. Ah, did I miss? I think, yeah, sorry, there was a 4 here. I hope that the number of the powers are correct, but it's given by this expression. Just to give you, again, a simplified picture, what is happening is basically you have this binary sitting on an orbit, it's emitting gravitational waves, but this adiabatic condition means that while it's emitting the gravitational waves, the system has the time to readjust into another circular orbit. This is basically the real meaning of adiabatic, okay? So you are passing to a nonion sequence of adiabatic circular spirals, and you are preventing. I mean, you are assuming that your system doesn't go from here to blue here, something which is drastically different from like an orbital configuration in this case. Okay, so given that I'm working this adiabatic approximation, what I have is that the loss of energy of my system is indeed given by the gravitational wave luminosity. This is responsible for changing the binding energy of the system. This contains indeed the Capillarian frequency, as we're going to see, L0, and so this will give us an equation for L0 now, which becomes a function of t, of time. So, for the system of interest, the energy of the system will be given by this, just a kinetic plus potential energy will be realized. I think I can cancel everything. And let's make a couple of simple calculations, a bit of algebra to see where we're going. So I take that expression there and let me compute the in dt, and what I get is gm mu over 2 L0 square dL0 in dt. And I can write this actually as minus E 1 over L0 dL0 in dt. Now what I really want to do, which is nicer, is express every change in terms of omega k, so the angular frequency of the system. So if I have omega k square, which is gm over L0, then if I do a bit of algebra and I differentiate, I get this. So I just differentiate this expression, which is this. And now if I isolate 1 L over L0 multiplied by the L0 in the t, and I equate these two, I get that 1 over L0 dL0 in dt is equal to minus 3 over 2 d omega k in dt 1 over omega k. Let's take this expression. Now let's plug this expression here inside there. So we have d in dt, which is 2 over 3 e over omega k d omega k in dt. And then let me write this. So omega is 2 pi, the frequency, so 2 pi divided by the orbital period. This basically tells me that this is minus 2 over 3 e 2 pi t over t square dt in dt. And so I find that dt, the variation of the orbital period with respect to time, because the system is losing energy to gravitational waves, is this. Instead of dt, d in dt, I put the source of my energy loss, and I get this. So that the change in the orbital period with respect to time, given by the gravitational wave emission, is given by this formula here. So if you observe a binary pulsar, for example, you observe the binary, you have the energy of the system if you can measure like its orbital parameter and masses. The gravitational, at least in GR, you get a prediction of how the gravitational wave luminosity depends as a function of the binary properties, and so you can fit the data and see whether the data actually reproduce your results. Okay, now in the last 4 minutes, and then we're going to complete everything later, tomorrow. So we saw that now everything is changed. Again, this T was fixed before because omega k was fixed. So for our frequency is changing because the orbit is, the system is jumping from one orbit to another orbit, closer and closer to the merger because it's emitting gravitational waves, and so the period is changing. Now, something nice we can compute is, okay, I'll cancel this. How L0 is changing. So how I want to find an expression for this. And let me go back to one of the equations that we wrote at the blackboard before. I think you have it on your notes. Which is this. And let me plug inside the gravitational wave luminosity, and I found that this is minus 64 over 5 I just plugged the expression that we have like for the energy. It was minus gm mu divided by L0, and this expression here, and simplified. This can be easily simplified. This depends on time. There is like L0 there, which depends on time, and you can easily bring L0 there and make the integral on both sides. And what we're gonna find is the following. The analytic integral of that expression will give L0 power of 4 of t minus L0 at t equals 0, which is the starting point of my observation, will be proportional to this. Now let me define a variable that I call tcol. I'll just explain what it is. So this is just the analytic solution of that equation there. There's nothing particularly fancy. And then, since I look at this, let me actually define this variable, tcol, which is given by this expression here. And if I cast this equation now in terms of tcol, I find a nice expression for L0 dt, also taking the 1/4 power of this expression, which is given by this. This basically gives you the evolution of the orbital distance between the two objects. Again, the orbital distance changes because there is a gravitational wave luminosity there, so the system is losing time. And you see that as time passes, these things, L0 t, becomes smaller and smaller, up to a certain point, because when t is equal to this value, that, I mean, now with a bit of imagination, we can call T coalescence, the gravitational wave, the orbital separation goes to 0. Now, tomorrow we will see that while the orbital separation goes to 0, as you actually expect, the gravitational wave and the orbital frequency that now changes in time diverges. Okay, now the point is that you'll never go with this approximation up to the coalescence, in the sense that all our assumption that we made will basically break way before T reaches T coalescence. But this is nice because it immediately gives a feeling, and I mean it's valid all of this in the weak field slow velocity motion approximation that we took, how that basically tells how the orbital distance decreases in time because the gravitational wave emission. Tomorrow we'll just complete this and we will compute how omega k now varies in time. And because omega k vary in times, even h mu nu, I mean, will be different, and I'm going to show you actually the final form of the waveform as a function, because you see now I have these as a function of the binary parameters, and now tomorrow I'm going to express the variation of the angular frequency in terms of the masses, and this will go into the waveform. Okay? That's it.